Now that you're familiar with three-dimensional space and plotting points and graphing, let's look at vectors in 3-space. And everything we do with vectors is going to be a logical extension of what we've done in 2 dimensions. So let's say I have 2 points in 3-space. The point A has coordinates 3, 0, negative 1, and B has coordinates 2, 1, 4. Write the component form of vector AB. You might want to hit pause, write your answer, and then check. So if you remember, component form, we do terminal minus initial. Another way of thinking about it is just looking at the individual coordinates. So to get from A to B, the x coordinate of A was 3 and the B coordinate was 2. So if we're at 3 on the x-axis and then we go backwards to 2, we've actually gone back 1 unit in the x direction. So that's a negative 1. Likewise, you look at the y's, we go from 0 to 1, so that's positive 1 in the y direction. And then we go negative 1 in the z direction to positive 4 in the z direction, so that's 5 units in the z direction. So once again, if you just do terminal minus initial, you'll get your vector, negative 1, 1, 5. Okay, so that was easy enough. That's just like what we do in 2-space. What if I ask you to write the vector AB in terms of the unit vectors I, j, and now k? Well, we know what I and j were in 2 dimensions. I was the vector 1, 0, so that's on the positive x-axis with a length of 1, or magnitude of 1. J was 0, 1 on the y-axis, so obviously k is going to be what? Now we're going to have to extend all these to 3 coordinates. So I is going to be 1, 0, 0, j is going to be 0, 1, 0, and then k will be 0, 0, 1. All right, so AB, instead of component form, we can write it as negative 1i plus 1j plus 5k. Easy enough. Find the magnitude of vector AB. Well, just like we did, we could do the distance formula between points A and B in 3-space. We proved how to come up with that formula. But if we just extend what we've learned, it's going to be the square root of the squares of the components of the vector. So negative 1 squared plus 1 squared, plus 1 squared, plus 5 squared. And so that's going to give us the square root of 27. 1 plus 1 is 2, plus 25 is 27. And then we can actually break that down a little bit. That's 9 times 3. So we can write that as 3 root 3. What else can we do? Let's say we have another vector v, which is 2, negative 3, negative 1. And we'll let w be our vector ab. So let me write that underneath. That was negative 1, 1, 5. Okay. Find w dot v. Well, how do you think we're going to do dot product in 3 dimensions? Just like we did before in 2 dimensions. It's going to be the sum of the product of the corresponding components. So it's going to be negative 1 times 2 plus the y's, which would be 1 times negative 3, plus the z components, 5 times negative 1. So we get negative 2 minus 3 is negative 5, minus 5 is negative 10. Let's double check. We had negative 2 minus 3 is negative 5, minus 5, negative 10. Check. We could also add or subtract vectors, just like we did in 2 dimensions. We can multiply by scalars, just like we did in 2 dimensions. And finally, what if I ask you to find the angle between these 2 vectors? Well, we know that the cosine of the angle between them is going to be the dot product divided by the product of the magnitudes. So that means that our angle theta between these 2 vectors will be their dot product, which is negative 10. over the magnitude of w, which was, I'll leave it unsimplified, the square root of 27. We already did that one. And then the magnitude of vector v will be the square root of 2 squared plus negative 3 squared plus negative 1 squared. So that's going to be 4 plus 9 plus 1. So that'll be the square root of 14. And then I'm going to need a calculator. And, oops, let's go back here. I don't want to leave off my, of course, it's not going to work. I have to do that. Move that over there. So theta is going to be the inverse cosine. I think I said it, but I didn't write it. Of all of that. And so now we'll grab our calculator and let's do second cosine negative 10 divided by the square root, and I'll combine these, 27 times 14. And that gives us an angle of 120.95 degrees, or we'll say approximately then 121.0 degrees. 121.0 degrees. And that's it. So everything we've done in 2 dimensions very naturally extends to 3 dimensions. So here are 2 key points to understand. And this works in 2 or 3 dimensions. 2 vectors, u and v, are parallel if and only if u is equal to c times v, where c is a constant. So in other words, if one of the vectors is a scalar multiple of the other vector, for example, negative 2, 1, 4, and the vector, I don't know, let's say 6, negative 3, negative 12. So if this is vector u and this is vector v, I know they're parallel because u is equal to negative 3 times v. So that's what we mean by a scalar multiple of each other. And then we also know that 2 vectors are going to be orthogonal or perpendicular, or sometimes we'll use the term normal, if and only if their dot product is 0. And just to make sure you understand, the if and only if means that this is a biconditional. So that means that if I tell you 2 vectors are orthogonal, you automatically know their dot product is 0. On the other hand, if I tell you that 2 vectors have a dot product equal to 0, you know that they're orthogonal.